I just have to put the other paper that was faxed?
Yeah, that'll work. It was emailed, but that's okay. Okay, for people who are interested, class hasn't started yet, but I'm going to answer Labor's question here, which is about the earthquakes. If you don't have a question about the earth...
That's like four, isn't it?
I don't know.
Number 4. Oh, we're just talking about that.
Okay, if you don't have a question about the earthquakes, you don't have to pay attention. If you do, well, we're going to look at it. So,
we are struggling on your homework.
the problem says that we have the speed for the P wave is 6 kilometers per second, and the speed for the S wave is 4 kilometers per second. And it tells us that the P wave arrives at 7 p.m. and the S wave arrives at 7:05 p.m. Are those the correct numbers?
Yeah, that's correct.
Because I'm obviously going on memory.
The S wave is slower than the P.
Yeah. So now that we have that, if we're talking about earthquakes, there are two things that we need to know to solve this. Well, 3, I guess. We need to know what speed is as well. But basically, we need to know that an earthquake occurs at the same location for both the S wave and the P wave. They both start at the same place, and we're receiving the same place, so they both travel the same distance, and they start at the same time. So, Holly, you can just be bored. We need to calculate the distance for each one because we know they're the same, and then we can set this distance as equal. So how do I find distance based on time and speed? Well, it's not cross, it's just multiply. The distance is equal to the speed multiplied by the time. So the distance for the S wave will be the speed for the S wave multiplied by the time for the S wave. We don't know what the time for the S wave from the earthquake to when it got us, or the time for the P wave from the earthquake to when it got to us. What do we know about those two times?
That they were within.
There's a difference of 5 minutes. So we know the time for the S wave is equal to the time for the P wave plus 5 minutes. I pay attention to the units and we'll see how it works out. They're the same distance, so I'm going to set the distances equal to each other and substitute for the time for the secondary wave. So doing those two things, I will have the speed of the primary wave multiplied by the time for the primary wave is equal to the speed for the secondary wave multiplied by time for the primary plus 5 minutes. I want to find the time for the primary, so at this point, I just need to solve for TP. So I will subtract VS TP from both sides. And then I have on the left side, time for the primary wave times V primary minus V secondary is equal to V secondary times 5 minutes. What's my last step? Well, you need to do your division before you plug them in. Okay, now Lauren Lee had asked about the units. You see now that as long as the units for the speeds are the same, the units are going to cancel out and I'll be left in units of minutes. So it doesn't matter what the units of these were, that's just going to be what the units are for my answer. So if you put in your numbers, well, at this time you should be able to put in the numbers easily enough and get what the time is. Now that's the time from when the earthquake occurred to when the primary was detected. So since the primary was detected at 7 p.m., you're going to have to subtract that time primary from 7 p.m. to find when the earthquake happened. You had a question?
Yeah, can you scroll back down? What's the minus the beat, the velocity s time p, like the second in the blue writing?
This that was the step in between. That was showing.
Well, how did you get to that?
I wanted to get the time p on the same side. So I had time p both here and here. And so I subtracted this one here. If you multiply the right-hand side through, that's VSTP plus VS times 5 minutes, right?
Yeah, right. Always 5.
And so I was subtracting this VSTP. So that,
sides.
yeah, from both sides. Now I have two equal signs, so that's why I have it 3 places now. So the purpose was to move the TP, so I had both TPs on the same side of my equal sign. Okay, now I went too long. It's 2 minutes past time to start. I do need to take record here real quick. Megan's here, Ken's here, Cody's here, Aline is here, Lauren Lane's here, Satish is here, Tioni's here, Sarah's here, Enrique. Looks like everybody's here. That's awesome. All right. Let me, instead of asking, is there another homework problem, let me go to homework problem number 6 because that's the one that requires the most amount of reasoning. So, homework problem number 6 is the problem that says angular momentum is given by an equation. It gives us L, well, it doesn't say L. L is the symbol we use for angular momentum. So the textbook tells us the angular momentum L is equal to mass times speed times radius. And then it tells us to use Newton's form of Kepler's third law. So Newton's form of Kepler's third law, if you read it in the textbook, the textbook writes it like this. If you look in, it says to look in Unit 17, and you find that in Unit 17. Now, to make sure that we don't have confusion, this D is the same thing as this R. And so I'm going to change that from a D to an R so that we don't have confusion about what the units are, or what the variables are, excuse me. And then the problem itself says, solve this to find, that's a D, to find speed as a function of radius. Now this requires us to do the same thing you had to do on problem 3, also the same thing you did on this lab. Right, in this lab it told you to find the speed, and I see here that Megan has written out very clearly, c is equal to 2 pi r, and speed is equal to distance over time, and thus circumference divided by a period. There's nothing to be embarrassed about there. I don't know why.
It's sunburned. It's sunburned. So.
Okay. So we're going to use exactly that, which, like I said, I believe that was problem 3, also had us doing that. And so speed is equal to the circumference, 2 pi r, divided by the period. I want to solve for speed as a function of r only, so that means I'm going to solve this equation here for period. So now I just have to do algebraic manipulation. That is, I'll multiply both sides by p squared and divide both sides by m to get p squared is equal to 4 pi squared over gm times r cubed. And then, of course, since that's p squared, I'll have to square root it. So I square root everything, and that gives me p is equal to, if you square root 4 pi squared, what's the square root of 4? 2. And what's the square root of pi squared? Pi. 2 pi, square root of r cubed. You can bring out an r, but you have to leave another r inside. And g and m stay inside. So that's my equation for the period that I put in right there, so that I will eliminate everything except for r. All I did was change the bottom part, right? The top part stayed the same.
None of it makes sense.
No.
Yeah.
It makes some sense.
Well, I mean, if you have the P and then you substitute the P into that.
Yeah. You're
I
putting
mean,
it
how we
in
got there doesn't make sense. It doesn't matter.
Yeah,
at this point.
yeah, I
Just
understand
know what-
substituting the P in, but
Okay, that's what I thought you were all objecting to. I'm like, really? So now, notice the 2 pi r over 2 pi r, those cancel. I'm left with 1 over square root of r over gm, which is more conveniently written as square root of gm over r. This should look very familiar because we already worked this out long ago. That was the equation for circular velocity. Right, that was, I believe, Unit 18, right after we had this in Unit 17. So now that I have this equation for the speed as a function of r, it tells me to substitute that in, substitute that into our equation for angular momentum right there. So my angular momentum, and nowhere does it tell you to use the symbol L for angular momentum. So it's not like you're supposed to know, oh, that's L. You can write out the words angular momentum if you want. L is just an abbreviation for it. It's mass times speed times radius. So that means I have the mass, and then for speed, I substitute what I just found, square root of gm over r times r. And now I'm going to bring everything into my square root. So that's going to be square root. When m goes in, it becomes m squared. M squared times m is, tell me, m cubed. So that's going to be square root of gm cubed. And then I had r. When it comes in, it'll be r squared. R squared divided by r. R. And so that's my equation for angular momentum as a function of radius. Now the question asks you, right, it tells you to do these steps, and then it asks you, so what happens to the angular momentum as the radius increases? Can you answer that now?
as the radius increases.
Yes.
What happens to the angular momentum as the radius increases?
As the r goes up, what happens to L?
I want to say that it gets bigger as well.
Yeah, because it's linearly, well, it's not linearly, it's directly proportional.
because they equal each other.
Yeah, because they're both on top, if you will.
They're not inverted over.
Yeah. And so that's what that one asks you to do. Caleb?
How did you get to the square root of gm cubed?
Okay, from this equation here, okay, this was the definition, here was substituting, and then I brought the m inside. But if you bring, if you bring 2 inside of a square root, you have to square it. So if I put 2 inside a square root, it becomes 4. So I put m inside the square root, it becomes m squared. But there was already an m here, so m times m squared gives me m cubed.
Oh, okay.
And likewise, this was r, bringing it inside, it's r squared. R squared, there was a divided by r, And so one of the R's cancels, leaving just one R on top. All righty. Now, let's start the lecture. Only 11 minutes late. Okay, we've already seen this slide. You remember this slide, right? Then we watched the video. Well, we're not going to watch a video here again. But we saw that video that showed all of the land masses moving and whatnot. Where does that come from? What kind of evidence could scientists possibly have to say that we had all of those funny Gondwanaland, Pangaea, Columbia, all those supercontinents in the past?
The rings of fire.
No.
We have reverse magnetic direction signature kind of in the rocks.
In the rocks of the ocean floor, we have magnetic fields that are frozen in place. Now, when I say frozen in place, that's really what it is. We talked last class period about the mid-oceanic ridges where magma is coming up, pushing the plates apart. And as it pushes the plates apart, new magma freezes, becoming new ocean floor. So we're constantly creating new ocean floor. What happens to the old ocean floor? It moves outward. Now, before any of that was known, we had sailors sailing the ocean blue. And sailors noticed crossing the ocean, their compasses would do crazy things. And of course, superstition might say, it's some kind of, sea monster or something. But scientists were like, why? Why would the compass not work? And so they went out and studied, and they found that the ocean floors had magnetic orientations that varied. And so, of course, the next thing you do as a scientist is you say, well, how does it vary? And so they go out and they measure exactly, because so here the magnetic field is pointing like this, and here it's like this. It's stronger here and weaker here, and they mapped it all out. And they noticed a couple things. Number one was that the pattern they saw on one side of the mid-oceanic ridge was the same as the pattern they saw on the other side. That makes simple sense with the interpretation that they're moving away from each other and building new floor in the middle. And then they said, okay, well, let's calculate the ages, use radiometric dating to calculate the age of the rock, and look at the orientation of the magnetic field. And the magnetic field that's stored in the rock must be the orientation of the Earth's magnetic field when the rock froze. And so by looking at the magnetic orientation and the strength of the orientation, they then can determine historical values for the Earth's magnetic field, both orientation and strength. They put together those pictures of the continents moving by looking at different times what the magnetic orientations were for rocks, and then trying to say, okay, so it must have been moving like this, and then we had a reversal, and so it's very complicated interpretation when you get down to it. But if you look at simplified fashion, it's like reading a cassette tape or a hard drive in a computer, right? They've just gone over with exactly the same type of a thing as you would to read a hard drive computer and read the ocean floor. And they've interpreted it with something that's actually more complicated than how we interpret the material on a hard drive. Hard drives just interpreted ones and zeros. And now our first clicker question, just to check if people have paid attention for the last 4 minutes. What evidence do scientists have for the large-scale motion of continents in the past? Okay, we had 0 to 10. Yeah.
Aren't I sure we were on the
Well,
It was
10,
me, wasn't it?
10 people were right. Never once did I say anything about fossils or fauna or fluvial. Fluvial means put down in a fluid. Fauna would be animal fossils. But that was not it. It was the magnetic fields in the ocean floors, what I've been talking about for the preceding 3 minutes. I'm a sad panda. Okay. Continuing on with the Earth's magnetic field information. The Earth's magnetic field looks similar to it would if you just had a regular old bar magnet there. So we can treat the Earth like it has a bar magnet in it. But there are some odd things to this. So let me just go to the next slide before I talk about the oddities. No, not that. Sorry. I thought it's the one after that, but I better go on before I get to that then. How does the Earth have a magnetic field? Well, if it looks like the magnetic field from a bar magnet, what would be the simplest answer to say what makes the Earth's magnetic field? A bar magnet. If it looks like a bar magnet, that's the simplest hypothesis to draw. But you have that hypothesis. Remember the whole scientific method. You have an observation. Hey, look, the Earth has a magnetic field. It looks like bar magnets. You have a hypothesis. Hey, must be created by something that's just like a bar magnet in the Earth. But then the next step is you have to have predictions made by that hypothesis and be able to test them. So, for instance, one of the predictions would be that the magnetic field should be pretty much constant, right? Because a bar magnet's magnetic field doesn't fluctuate. But then if you go and you study, as we saw, the magnetic fields have fluctuated a lot. So that hypothesis fails. So then it's back to develop a new hypothesis that takes into account the fact that the magnetic field fluctuates, gets stronger, weaker, and changes direction. And as scientists thought about that, they said, well, we do know that moving charged particles creates a magnetic field. So if I have moving charged particles, that create a magnetic field. More specifically, if they're going in a circle, it would make a magnetic field. And so they said we must have these charged particles swirling inside the Earth. So there must be a molten part that's swirling to make our magnetic field. And so that theory is called the geodynamo, which I know is written here somewhere. Well, it says magnetic dynamo here, but because it's the Earth, it's a geodynamo, to create the Earth's magnetic field. Now our second clicker question.
Just one or just one answer?
It should be just one answer, I believe. Somebody who's answered like, yeah, Lauren Lee, you just press one answer, right? You didn't have to press enter. Yeah.
You just say that they do protect us from the sun's harmful ray or something.
Okay, we had 0, 1, 5, 6. Well, this one wasn't as clear. Talk to your friends and neighbors, so they turn around and talk to the gentleman behind you, about what you answered and why.
Well, since nobody wants to answer, I answered that there was a city course.
Why?
Well, obviously I don't think that there's a permanent magnet in the course. Also, it's not a permanent magnet on the surface.
That's all I'm thinking.
Have you ever taken apart? I'm over. I sure have. One of my favorite motors in this realm is electrical motors. Seem pretty straightforward.
Okay, let's answer again. We're going to do it again. And this time, Hopefully people are going to answer more correctly. Be more like Sarah and, well, everyone who's answered so far. Be like them.
So answer again right now?
Yes.
But the right way.
Well,
I'm really tempted to put G down. Just to make it so where Dr. Webb can't sleep at night.
It's horrible.
Okay.
That would be more fascinating.
this time we did better. The last person in ruined a perfect set.
Dang it, Dylan.
I got you this time.
Okay. Remember, what was the scientific evidence I gave you why it could not be C?
Because they didn't, like, right, does it relate to yesterday when you're talking about S waves and P waves and
That's how we know it's not salt.
That's not what I just gave right now.
Yeah.
I mean, that would be a relevant argument as well.
But if it were a permanent magnet, then we wouldn't have fluctuation.
Yeah, if it was a permanent magnet, we wouldn't be having the fluctuations
Oh, right.
and reversals of the magnetic field.
Right.
With fluctuation.
Excuse me?
Fluctuation.
With fluctuation.
Which fluctuations?
What
The-
is that? What is that?
Oh, okay. Fluctuations are variations.
Oh,
So, it turns out to be 2 slides, we'll have a picture that shows some of the fluctuations. The Earth's magnetic field, if you look at it in more detail, it's not as much like a bar magnet as you would expect, but it's because the sun's cosmic rays do interact with our magnetic field and change the shape. So the picture on the right, the big one, shows the Earth's magnetosphere as we believe it exists. And what you notice is if you stay close to the Earth, that is, if you stay within a region, something like this, it looks pretty much like a bar magnet would. It's pretty uniform. But if you get bigger, you see that uniformity completely disappears, that it's really elongated. And the reason is because the sun is blowing off copious amounts of charged material. Things like protons are coming flying at us from the sun. And those protons, and I think I heard Labor talking about this, I heard somebody talking about it, those charged particles interact with our Earth's magnetic field. And so they compress it on the front side. The magnetic field deflects them away so we don't get nearly as much radiation from the sun. That's the types of radiation that would be harmful to us, like charged particles hitting us, that we would without the Earth's magnetic field. Interestingly enough, the magnetic field lines actually would make charged particles that are coming like this spiral around and come into the pole. And so you actually get charged particles that are directed into the poles. That's what causes northern and southern lights. The corona borealis and corona australis are caused by charged particles from the sun coming into the Earth's atmosphere, exciting electrons and atoms high in the atmosphere. They de-excite and give off light. When you have enough of that, you can see it, and we call it the northern lights or the southern lights. And then those charged particles make the magnetic field really elongated. Very interesting, at least to me. Another very interesting thing is the Earth's north pole is its south magnetic pole. And the reason is because the poles were originally named, I take a bar magnet, and this side points to the north of the Earth. And so they said, well, I'm going to call the side of the bar magnet that goes toward the north of the Earth the North Pole. But then further study says that the North Pole is attracted to a south magnetic pole. Opposite poles attract. So if the North Pole of the magnet is named the North Pole because it's attracted to the Earth's North Pole, that means the Earth's North Pole that it's attracted to has to be a magnetic South Pole. Kind of crazy, isn't it? But fear not. Fear not. We have the future coming. In the coming years, the Earth's magnetic field will reverse. And the North Pole will become a North magnetic pole. If you look at the graph here, the top one is showing a very large time scale. The ages here are in
Million years.
mega ages, which means million years, yes. And so you're looking there, and the Earth's magnetic field, according to this graph, which I believe is correct, hasn't changed in about 5, 6, 7.5 million years. Million years? No, 750,000 years, because it's less than 1. So it's been about 750,000 years since the Earth's magnetic field has changed. If you look up here, you see that there have been a lot of magnetic field changes over time. There has been an extremely long period. I'm still in white. It's like, where's my mark? There is an extremely long period here where it stayed the same. So we are nowhere near that long period. I mean, you count that up and you have what? 10, 20, 30, around 40 million years where it appears the Earth's magnetic field stayed the same. And we're only 750,000 years. But the average is about 200,000 years and it flips. So we're actually well over the average time before the Earth's magnetic field would flip. And this graph right here is showing what happens to the strength of the Earth's magnetic field coming into a change in magnetic field. And there are some people who interpret this to say, yeah, we might be just a few, tens of thousands of years from a magnetic flip for the Earth. We don't know enough to be able to make a reliable prediction there. Question?
So what does that practically mean? Like if we were to be alive when the
Okay,
poles were...
what does that practically mean? You might have seen some stupid movies.
Like the core.
Like The Core. And one of the things that is typical of that kind of movie is the birds go crazy, right? The birds just en masse fly into the walls of a building, right? Does that happen in The Core? It's one of those movies.
Yeah, it does. Those
Yeah.
are glass buildings, but close enough.
Yeah, well, I don't care. They all fly into
I
water.
really didn't care either.
Yeah.
Now, there are massive bird die-offs for random reasons. They apparently, the bird brain thing is not
Too far from
Yeah, not too far from the truth. But the fact is, birds use the magnetic field as one of their navigation things. Interestingly enough, bees use the polarization of light. Which is really cool. What? Yeah, no, it is. Don't mock.
No. I actually thought that was really cool.
Okay.
I'm not to nerd out over here.
So animals that use magnetic fields for migration, yeah, it will mess with them. But it's a slow enough process for the magnetic field decreasing in strength. I assume that they will figure out other ways to migrate. This whole compass thing isn't working for me anymore. Maybe I'll go to, visual reckoning. I'll look at the star. I don't know. I can't speak for the animals, but
I think butterflies are going to look at the stars.
You just speak. That's
thank you, Sylvia. I'll let you come up and do the speaking for He's the animal whisperer. Come here.
I have the voice.
Okay, so that's probably ridiculous. But what is more legit is we have the protection from the solar radiation, that is the charged particles of the solar wind, and that protection would disappear.
So
Now,
we'd be dead before we could adapt.
not necessarily dead. I am a man who believes in creation, right? I believe that God created the different types of animals and so on. But if I believed in evolution, I would take this as part of my evolutionary theory and say that we should have punctuated evolution. Because if we didn't have that magnetosphere, we'd have a lot of charged particles coming in and hitting us. And those charged particles will do things like break molecules apart. And if they break molecules apart in your DNA, then it could reform correctly or it could reform incorrectly. If it reforms incorrectly, it could, whatever damage could die, or you could have a mutation.
Yes. Excellent.
And so,
Yes.
so one would expect mutation rates to jump at the times when the Earth's magnetic field is flipping. And so I would expect, if I believed in evolution, a punctuated evolution where things are just barely changing, then you have a bunch of changes and things are barely changing, a bunch of changes, because of suddenly having a time frame where you have a lot of mutations occur.
So then that big black spot is a Cretaceous period. I get it.
Actually, Cretaceous period
It was like close.
is more like, I think, here to here. It's like yeah, I would have to go look at that again. I require my students every year to memorize it, and then I don't. Okay, moving forward.
Teacher confessions.
Require them to memorize them if it's not important enough for you to memorize.
Huh. Well, I actually each year go through and memorize it, and then I just forget because I just put it into short-term memory so I don't look stupid when the students ask, when was the Cambrian? Oh, it was up till 541 million years ago. Duh. Yeah.
Not so dumb.
Okay, so moving on to water. Water is an important part of the earth. 71% of the earth is covered. So important that my next slide has a lot of duplication from this slide. One of the things that I want to keep from this slide is water acts to store carbon dioxide, which is an important greenhouse gas. We're going to talk about the greenhouse effect here, and that's a very important feature. Water also causes a lot of changes to the surface of the earth. I don't know what that's about. I don't know what happened to the rest of my presentation. I thought that there was something wrong. There are 27 pages, and that's all that came up. Not no more class. I am just going to... I can do it freestyle, but I'm not going to do that either. I'm going to just change over to this. I'm going to change your 2 clicker questions you've answered. Yes,
So what was it again? Water on Earth's surface to trap carbon dioxide? Is that the thing?
Yes, it does. And let me just open up the presentation on this computer. I don't know what happened. Okay, slideshow, presenter view, excellent. That doesn't look like it's showing up there. Why does this happen? Everything go flashy, now come up. There we go. Okay, so I won't be doing any more writing, instead I'll have to be clicking on this. I don't know if we want to keep the audio rolling here or not. Okay, so this is the slide we left off on. The Earth's hydrosphere is the water. Then we have above the water the atmosphere. And most of the atmosphere, or the mass of the atmosphere, is very tiny compared to the mass of the Earth, right? The total mass of the Earth, it's just 1/1,000,000th of the mass of the Earth is in its atmosphere. But the atmosphere is really kind of important to us. Because, well, you know, we can't breathe without having it. So, and there's an unfortunate thing here, but let's just move on. There's a certain atmospheric pressure, about 14.7 pounds per square inch, PSI, or about 101,300 newtons per square meter, or pascals. So what causes that air pressure?
Gravity.
Gravity. It is caused by gravity pulling the air molecules down. And all of the air molecules above you, they have mass, so they have weight. So the air pressure is the result of the weight of all the air molecules above you. Now, of course, you might say, wait, I'm inside the building now. Well, there are connections from the building air to the outside air, and so the pressure goes around those boundaries. So the air pressure is simply caused by the weight of the air above us. And so this picture here is illustrating pillows. The lower ones are supposed to be compressed by the weight of the ones above. I somehow think that they might have, modified things a little, but yeah. On the left are pillows. On the right, that's a graphic that's illustrating the same thing. Now, I'm really curious as to what's going to happen. Yeah, you're going to see the same thing I'm going to see, which is nothing at this point. What causes the air pressure we feel? Well, you guys are answering. Let me. Definitely B. Okay, I have 12 responses. There's 13 now. And great, it's not showing me. That's just the life.
It's okay, we already said it's C.
It's the dog and I couldn't help see.
Yeah, it's definitely C.
I was waiting for him.
Okay, the answer is not C.
It's A.
The answer is yes, A. Everything is going perfect. Yeah, there were 33 slides, and of them you saw 9. Well, at least you can see from these that I have the slides. So, talking about that air, we have the layers here. We have the lowest layer is the troposphere. And what do we have in the troposphere? Well, we have our weather patterns that you and I are accustomed to. We have airplanes flying about. We have birds. It's not very tall, right? Only about 12 kilometers upward. And it's interesting to note what happens with the temperatures all the way up. The temperatures are initially getting very cold as you go up. So if you're at the top of Mount Everest, which doesn't make it out of the troposphere, but it is pretty tall, it's what, 8 kilometers or more? So you're getting up there. You have a much colder temperature, hence people freeze up there. And you have a lot less air pressure because there's a lot less air above you. Hence, it's hard to get enough oxygen because you don't have enough air there because it's not being compressed. And so people die from lack of oxygen. Or to put it another way, when you climb Mount Everest, you're going to die if you don't do it just right. They have a region they call the kill zone. I heard the death zone. You can't live there. You can go up there and come back down as long as you keep it short enough that you haven't died yet. Okay. Did you have a question, Megan or Sarah? I thought we did. No.
Surely a mountain without mercy.
Yes. Okay, next above that is the stratosphere. Now, I always think of the stratosphere as the high reaches of the atmosphere. Now, this is, by the way, a simplified view. There are other views that put in more layers. So this is kind of a simplified view. The stratosphere goes up to about 50 kilometers, and notice the temperatures start going back up. So it gets warmer as you go up in the stratosphere. And you see that maximum ozone? The ozone layer is important to us. The ozone layer blocks ultraviolet radiation from the sun. It absorbs ultraviolet radiation, which breaks bonds in the ozone. Without the ozone layer, we would get more ultraviolet radiation, more suntan/sunburn, more skin cancers. So that ozone layer is important to us. And of course, being an environmentally friendly, conservative person nonetheless, we want to keep that ozone layer there. So we do things like make our air conditioners work pretty poorly compared to what they could do because the chlorofluorocarbons that we use as air conditioning fluid, the Freon, it breaks down the ozone in the atmosphere and thus it's bad for the environment. Question?
So I've heard like there's holes in the ozone layer. Like,
Yeah.
how does that even come about? Like,
Okay, they're actually seasonal. That is, when it's summer in the southern hemisphere, an ozone layer forms over the southern hemisphere. Now, I think there are years that it hasn't completely formed, which is good. But what's going on is you have the solar radiation, which is breaking up the ozone. And if the ozone wasn't fully refilled because of things like chlorofluorocarbons, then you could break enough of it up that you actually have a hole, and then you're getting just raw ultraviolet light coming through without any filtering at all. The thinner it is, the more you're getting through. And so that's, of course, considered a bad thing for us.
yeah.
Is that in Antarctica? That happens?
It's, I don't remember its location exactly, but it's somewhere in that vicinity. Yeah. Okay, you get up above the stratosphere and you get to the ionosphere. And the ionosphere, you see temperatures get cold, then they get warm again. Really crazy. The ionosphere is where we see things like our northern lights and comets. So that's where we see some interesting things in the atmosphere. It's also important, let's say that you're a ham radio operator. You like to get on that radio and you want to talk to somebody that's, on the other side of the world. The ionosphere helps you do that because your radio waves will come up. It's called the ionosphere because you have ionized gas. The ionized gas is conducting, and so your radio waves will actually come and bounce off of it. Hence, you might hear people talk about bounces or skips when they're talking about radio. Like, I was one summer up in Wyoming, and I could listen to baseball games in Los Angeles because I was getting skips of the AM radio stations off of the atmosphere. So, this is the talk about the ionosphere. Another clicker question that I won't be able to see your answers for, but put your answer down there so you can put yourself on a number before I talk about the correct answer. What is the correct order? Yeah. I downloaded again, and once again, it didn't do all of them, so forget that. Got 10 people have answered. All but one. Can't tell who. Okay, going on. Okay, so the correct order here, the lowest one is the troposphere. Next is the stratosphere, and highest the ionosphere. How could you remember that? Well, obviously we just went over it, so I'm remembering because I just went over it. But another way is to do it in alphabetical order. From the highest down, it's ionosphere, stratosphere, troposphere. That's alphabetical order if you start at the highest and go down. Okay, the aurora or northern lights. Here we see in the diagram how the charged particles from the sun spiral around magnetic field lines and come in at the poles. And so it's those charged particles coming into the ionosphere that give us those auroras, the beautiful colors. And the color depends on the gas that is being excited. Now, how would you ever know if there are northern lights visible here?
You can tell you the radio station.
You would see them. You would be told on a radio station possibly. Or you can simply go to that website, Space Weather, and see a weather report for, will there be auroras visible in my region? And it'll let you know. We can predict these things because it comes from the sun, and during normal solar activity, you don't have them. But when you have the sun is extra active, that is like you had a storm that shot out a jet of charged particles at the Earth, well then we're going to get them when those get to us. And so they monitor, space weather is monitoring what's going on with the sun mostly. And when the sun has an ejection, a flare or a coronal mass ejection, if that's going to hit the Earth, then they say, oh, this is going to hit the Earth, it's going to have this many particles per second. It's likely then to make aurora that's visible for this range. And if you sign up as a member to the site, they'll send you a text alert. It used to be free. To alert you anytime that there are going to be auroras possibly visible in your area.
So, little off topic, but why do the auroras look like vertical strips?
I can't answer that. I don't know. This does answer Labor's question, though. Where's the hole in the ozone layer? Apparently over Antarctica, like Labor said.
Sorry for the penguins.
Yeah, the poor guys. I'm going to go past this to talking about the greenhouse effect because we only got 6 minutes left here. The greenhouse effect is real. I've said this before, but I will say it again. What would happen to us if there was no greenhouse effect?
Well, we'd lose all of our
We'd
heat.
get a lot of cancers and there'd be Earth will really start to heat up.
That is, yeah. If there was no greenhouse effect, we'd be popsicles. We'd freeze. We'd be similar to Mars. It would get, some places on Mars it's warm enough that it would be comfortable. No place on Mars is it hot. and many places on Mars would be popsicles. And so if the Earth didn't have a greenhouse effect, we'd all freeze. We need to have the greenhouse effect. But of course, needing to have the greenhouse effect is kind of like saying, I need to eat food to live. There's a limit. If I eat too much food, I might grow obese. I might. So, with the same thing occurs with the greenhouse effect. Too much greenhouse effect, what do we become? Like Venus. Right, so too much greenhouse effect like Venus. Too little greenhouse effect like Mars. Just right like us. Labor.
Doesn't Venus have stronger chemical properties on the atmosphere that traps greenhouse gases?
Well, it has a lot more greenhouse gases, methane, predominantly, I believe.
Earth doesn't have that.
And so that's why it has a runaway greenhouse effect. We have a lot of potential greenhouse gases have been locked away in liquid water. Now, water is, in fact, the strongest of our greenhouse gases, water vapor. But if it's cool enough for water to mostly be liquid form, then that's not a big problem. If it warms up and you have more water vapor, that would be a bigger greenhouse problem. At the same time, if you look at this picture, you have light comes in, notice light hitting ozone and being absorbed. That's the process of the ozone. Some light comes down and hits clouds and gets reflected. I'm not seeing a place here where it shows reflection, actually.
Yeah, right.
Oh, yeah, here, okay. It reflects off the clouds. So while water is a very strong, the strongest, greenhouse gas, it also, if you have a lot of white water vapor, it forms clouds, which reflects the radiation, keeping it from getting in. Now, what's the greenhouse effect? The greenhouse effect is that the radiation that gets into the Earth tends to be visible light. Right? We have the sun gives off the majority of its radiation in the visible spectrum, and the Earth's atmosphere is transparent to visible light, so solar radiation just comes right in. Gates open. It's absorbed by the Earth, and the Earth emits, remember we learned Wien's law that the peak wavelength is equal to 2.7 million nanometers times Kelvin over the temperature. Well, the Earth's surface temperature is around 300 kelvins, which makes the Earth radiate about the same as you and I do. Not visible, infrared. And so the Earth is giving off radiation in infrared. Now, if the radiation the Earth gives off is equal in value to the radiation it absorbs, the temperature will stay constant. If it receives more radiation than it emits, then it will start getting hot. If it emits more radiation than it receives, it will start getting cold. So the greenhouse effect blocks some radiation from leaving. So we have to absorb more radiation. The Earth gets hotter. As it gets hotter, it gives off more radiation. Remember, we also learned from the Stefan Boltzmann law that the radiation is proportional to temperature raised to the fourth power. So if the Earth heats up just a little bit, the radiation goes up by a lot. And so you work to reach a balance where the radiation coming in is equal to the radiation that's allowed out of the atmosphere. And if you have more gases up there that are going to absorb the radiation and not let it out, then the Earth's temperature correspondingly has to go up. So that's what the greenhouse effect is. And like I said, it's absolutely necessary for life on Earth. Why is it such a big deal then in the media? Because man can affect the amounts of carbon dioxide in the atmosphere. That's the one that we have the biggest effect on. Now, of course, you've probably read about Cal Flatulence putting methane into the atmosphere. That research study was done at Washington State University. They don't call us a Cal College for nothing. And it is a significant greenhouse factor. People who eat meat, you can point your finger at them and say it's your fault that we have a greenhouse problem. If we believe it's your fault. Because
Small price to pay.
the cattle and all of the agriculture that's necessary to feed the cattle, far more than would be necessary to just raise things for vegetarians, is a significant contributor to the man-made portions. Okay, yes, it's time to go. And remember, there will